Cosmic silence is the canvas upon which the universe paints its most enigmatic spectacles, and in the emptiness beyond the familiar stars, 3i Atlas erupted into a theatre of chaos unlike any astronomer had witnessed. From the dim edges of the solar system, it appeared first as a faint, wandering speck, an interloper in a domain governed by predictable gravitational choreography. Yet, as days passed, something extraordinary began to unfold. The object's trajectory wavered unpredictably, shimmering with bursts of light that defied its previously calculated path, as if the very cosmos around it had become unstable. It was not merely an anomaly, it was an affront to expectation, a riddle inscribed across the night sky, inviting both awe and dread. The sensation among the observing community was immediate and profound. Observatories from Chile to Hawaii, from the deserts of Arizona to the peaks of the Canary Islands, turned their instruments toward this single point of luminous uncertainty. Telescopes captured unexpected oscillations in brightness brief, violent pulses that suggested rotations or reflections not consistent with known cometry or asteroidal behavior. Astronomers murmured among themselves, voices tense with excitement and disbelief, as the initial data hinted at properties that seemed almost alive, fluctuating, erratic, yet following a pattern that evaded comprehension. In those moments, 3i Atlas was no longer a distant rock. It became an actor in a cosmic drama, performing a narrative written in light, motion, and space itself. Philosophically, the event struck a chord deeper than scientific curiosity. Humanity, long accustomed to the comfort of predictable celestial mechanics, faced the sudden reminder of its smallness and vulnerability in the infinite void. What force could alter an object so thoroughly? Was it a natural anomaly, the result of processes yet undetected, or was it something more, a hint of intelligence embedded in the cosmos? The mind, confronted by such magnitude, tends toward awe, fear, and reflection in equal measure. Observers described moments of existential vertigo, staring at the live feed data, realizing that the universe could be stranger than any imagination, richer in possibility and terror than previously dared to consider. Every photon captured by the sensitive arrays of telescopes became a messenger, carrying with it the silent testimony of events occurring millions of kilometers away. Each spectral line, each minuscule wobble in the object's path, was a syllable in a language not yet deciphered. It was as if space itself had exhaled, revealing a glimpse of hidden mechanics and inscrutable design. For the astronomers, physicists, and theorists who first glimpsed the anomaly, the sensation was cinematic. The vast emptiness of interstellar space suddenly contracted into a scene of profound drama, where light and matter intertwined in a spectacle both terrifying and magnificent. Here, at this cosmic threshold, 3i Atlas beckoned humanity to look closer, to question assumptions, and to confront the raw, unfiltered mystery of the universe. The emotional resonance extended beyond the scientific community. In quiet homes, people followed live feeds, watched animated trajectory models, and read early press briefings. The object's erratic behavior sparked debates in forums, discussions on late-night radio, and contemplations under city lights, where the night sky usually offered only calm constancy. And yet, despite this sudden attention, the object remained remote, untouchable, a reminder that the universe's mysteries do not bend to human desire for comprehension. It was both a challenge and a revelation, a signal that the cosmos is not static, and that even in the familiar theatre of the solar system, there can appear forces, objects, and phenomena that confront the limits of knowledge and imagination. The stage was set for a story that would span the gamut of human inquiry, from empirical measurement to philosophical rumination. The eruption of chaos around 3i Atlas marked the beginning of an investigation that would test instruments, challenge theories, and stretch the mind to consider the unimaginable. Here, in the silent reaches of space, the interplay of motion, light, and energy announced itself not as a mere astronomical curiosity, but as a narrative demanding attention, patience, and reflection. And in that quiet tension, humanity glimpsed a universe both beautiful and ungovernable, where every discovery is a doorway to deeper mystery, and where one small speck of matter can erupt into cosmic significance. The story of 3I Atlas's discovery is inseparable from the meticulous work of astronomers scanning the heavens for objects both familiar and foreign. It was during the quiet hours of an early October night that the first hint of the anomaly emerged, a faint, elongated point of light that did not conform to the predictable motion of the countless asteroids and comets catalogued over decades. Initially, it was almost dismissed, lost among the routine measurements and background noise. Yet, as data accumulated, the uniqueness of 3I Atlas could no longer be ignored. The discovery was not a single moment, but a confluence of careful observation, serendipity, and the perseverance of those who dedicate their lives to seeing what others often overlook. The first detection came from the Pan-STARRS Observatory in Hawaii, a facility designed to patrol the skies with precision and diligence. The survey cameras, scanning vast swaths of the night sky, recorded the object's subtle motion against the distant stars. The initial analysts noted its hyperbolic trajectory, immediately recognizing that this was not a typical solar system resident. Unlike the elliptical orbits of comets and asteroids bound by the sun's gravity, 3 Atlas appeared to be visiting from interstellar space, tracing a path that suggested it had come from distant reaches beyond our planetary neighborhood. The realization sent ripples through the astronomical community. Interstellar visitors are rare, and their detection is a testament to both human ingenuity and cosmic chance. Key figures emerged in this discovery. The lead astronomers who processed the data were familiar with the cadence of the cosmos, accustomed to filtering out false positives and mundane artifacts. Yet, the motion of 3I Atlas resisted classification. Its speed and incoming angle prompted immediate comparisons with the previous interstellar visitor, Oumuamua, which had sparked global curiosity merely a few years prior. Yet even then, 3I Atlas distinguished itself through its sheer unpredictability, its subtle brightness variations, and the mysterious irregularities that would soon become the focus of intense scrutiny. These scientists, often working through long nights, were the first to perceive that something extraordinary had entered the solar system's quiet orbit. The conditions of the discovery were emblematic of modern observational astronomy. Advanced algorithms sifted through terabytes of imaging data, separating stationary stars from moving objects and identifying potential anomalies with precision. When 3I Atlas's track was plotted against expected celestial motions, the deviation became unmistakable. It was not merely passing through, it seemed to carry an energy and rhythm that defied conventional explanations. For the teams involved, there was a thrill akin to listening to the first notes of a symphony yet to be composed, where the instrument was the universe itself and the melody, a series of enigmatic motions etched across space. Public announcement followed swiftly, with journals and scientific bulletins outlining the initial observations. Scientists spoke cautiously, aware of the tendency to anthropomorphize or overstate discoveries in the early stages. Nevertheless, the evidence was compelling. This was an interstellar visitor whose behavior challenged standard models and whose existence prompted new questions about the frequency, origin, and nature of objects from beyond our solar system. In laboratories and observatories worldwide, telescopes were reoriented, spectrometers recalibrated, and observation schedules rewritten all to capture as much information as possible before the object continued its fleeting journey. The narrative of discovery, though rooted in data and instrumentation, also carries an emotional undercurrent. The astronomers felt a quiet awe, a recognition that they were witnesses to a phenomenon that humanity had only glimpsed once before. There was humility in the face of the vast unknown, tempered by excitement and the drive to understand. The discovery of 3I Atlas was more than a technical achievement. It was a reminder that the universe is dynamic, unpredictable, and capable of presenting enigmas that force humans to expand both knowledge and imagination. From that first faint glimmer on Pan-STARRS' sensors, a story of cosmic chaos, scientific intrigue, and philosophical wonder began to unfold, marking the starting point of a journey that would traverse observation, theory, and contemplation alike. The first wave of scientific analysis brought astonishment and, for many, a quiet sense of dread. The initial measurements of 3I Atlas revealed velocities and rotational patterns that strained the bounds of expectation. Classical mechanics, which had served as a reliable guide to celestial motions for centuries, seemed inadequate to fully account for the object's behavior. It was as if the rules that governed comets, asteroids, and interplanetary debris were being bent, twisted, or temporarily suspended. Every calculation seemed to highlight inconsistencies. The hyperbolic speed suggested a visit from distant stars, but minor deviations in its path hinted at unseen influences. Scientists were forced to confront the reality that this was no ordinary interstellar traveler. It was a riddle, a paradox, a challenge to the very frameworks used to interpret the cosmos. The strangeness began with 3I Atlas's acceleration. Unlike other interstellar objects, which largely follow predictable trajectories dictated by gravity and minimal outgassing, 3I Atlas displayed subtle yet measurable changes in velocity, uncorrelated with solar radiation pressure or known forces. Instruments detected small but rapid fluctuations, as if the object were responding to conditions in ways not yet understood. This behavior invited immediate comparisons with Oumuamua, whose acceleration had sparked debate over potential natural and artificial explanations. But while Oumuamua was enigmatic, 3I Atlas seemed actively defiant its erratic shifts, suggesting a dynamic entity interacting with its environment on multiple levels. Equally unsettling were its optical characteristics. Observers noted unusual reflective properties, brightness variations inconsistent with simple tumbling or rotation. The surface, if indeed it was solid, appeared to possess patches of differing albedo, reflecting light in irregular bursts. For astrophysicists, this implied either complex compositional heterogeneity or perhaps some mechanism producing transient luminescence. Even seasoned experts, familiar with the oddities of space, found themselves recalibrating expectations. The observational data seemed almost alive, not in a conscious sense, but in its unpredictability and capacity to contradict prior models. Here was a body that existed outside the comfort zone of established astrophysics, a tangible reminder that the cosmos harbors behaviors that challenge comprehension. The challenge extended to gravitational analysis. As 3I Atlas approached the inner solar system, its path could not be fully reconciled with the positions of planets, minor bodies, or solar perturbations. Standard N-body simulations failed to predict subtle course deviations, prompting re-evaluation of underlying assumptions. Could interactions with dark matter streams be influencing the motion? Were magnetic fields playing a more significant role than anticipated? Every hypothesis carried caveats, and each simulation seemed to reinforce the extraordinary nature of the observation. For the scientific community, this was both thrilling and terrifying. to witness a natural object that might reveal entirely new physics, yet remain frustratingly elusive to analysis. Adding to the tension were spectral readings. Early spectroscopic analysis suggested the presence of unusual chemical signatures, elements or compounds not typically associated with known interstellar objects. The data hinted at an interplay between radiation, composition, and motion that further complicated the picture. Were these anomalies the result of exotic ices, high-energy irradiation, or interactions with interstellar gas and dust? The implications were staggering. Every unexplained data point suggested either a gap in understanding or, more provocatively, the influence of factors previously unconsidered in celestial mechanics. Emotionally, the scientific shock reverberated beyond technical circles. Research teams worked around the clock, sifting through data, running cross-checks, and debating interpretations. Even within peer-reviewed journals, the language was cautious but imbued with wonder. Headlines spoke of a cosmic puzzle or a mystery visitor, reflecting both public fascination and professional awe. For physicists, astronomers, and theorists, 3I Atlas became a mirror, reflecting the limits of current knowledge and the tantalizing promise of discovery. It was a phenomenon that simultaneously humbled and inspired, a tangible encounter with the unknown that demanded both meticulous scrutiny and philosophical reflection. In its contradictions and surprises, 3I Atlas had firmly established itself as one of the most confounding celestial events in modern astronomy. As observations intensified, patterns within the chaos began to emerge, subtle and tantalizing, hinting at structures or behaviors that defied initial expectations. While the object's motion appeared erratic on a first glance, careful analysis revealed oscillations, tiny periodic shifts in trajectory, minute but persistent rotations of brightness that suggested a complex internal or external interaction. These patterns were not immediately obvious, hidden within layers of noise and distortion, and only through the patient work of astronomers and computational astrophysicists did they begin to take shape. What had first seemed random was now suggestive of underlying rules, obscure and uncharted, that hinted at a mechanism far more intricate than a simple tumbling rock or a conventional comet. The instrumentation employed was crucial to this discovery. Ground-based telescopes equipped with high-resolution spectrometers measured the minute changes in reflected light, allowing scientists to map albedo variations across the object's surface. Space-based observatories, including those designed for infrared and ultraviolet detection, provided a complementary perspective, revealing transient emissions and energetic anomalies that were invisible to optical sensors. Particle detectors and cosmic ray observatories noted subtle interactions between 3I Atlas and surrounding interstellar matter, registering fleeting energy releases that added layers to the puzzle. The combination of these instruments transformed a dim point of light into a multi-dimensional object, revealing not only its movement but hints of composition, rotation, and perhaps even surface morphology. One striking feature was the appearance of rotational modulation. By observing the light curve over successive days, astronomers noted fluctuations that suggested 3I Atlas rotated irregularly, with periods that did not conform to simple spin or tumbling models. This implied that the object's mass distribution might be uneven, or that it possessed active forces affecting its rotation. The discovery sparked immediate discussions among theorists. Could sublimation of volatile materials explain these rotations, as seen in traditional comets, or was there an altogether different phenomenon at play, one that had not been encountered in any other interstellar visitor? The spectral data added another layer of intrigue. Ultraviolet and infrared readings indicated the presence of exotic materials, compounds, and elements that, while not impossible, were uncommon in interstellar space. Scientists speculated that cosmic irradiation, high-velocity particle interactions, or even unusual ice mixtures could account for some of the signatures. Yet certain peaks in the spectrum remained unexplained, suggesting chemical or physical processes previously unobserved. These anomalies reinforced the idea that 3I Atlas was not merely an interstellar asteroid, but a probe into the unknown, carrying encoded clues about the physics of far-flung regions and the possible histories of objects traveling between stars. Patterns also appeared in the object's interaction with radiation. Minute deviations in velocity correlated with solar wind pressure and electromagnetic forces in ways that resisted conventional calculation. Some researchers proposed that the object's surface might be unevenly reflective, or that charged particles on its exterior created feedback with magnetic fields encountered en route. These emergent patterns hinted at complex couplings between mass, momentum, and energy interactions that blurred the boundary between a passive celestial object and one with quasi-dynamic properties. Even the most conservative theorists could not ignore the suggestion that 3I Atlas behaved in ways previously thought impossible, straddling the line between natural and anomalous. By the end of this phase, the deeper investigation had transformed the initial curiosity into a profound scientific challenge. What had first seemed a solitary, fleeting anomaly now revealed itself as a structured enigma layered with rotational, spectral, and dynamic complexity. Patterns within the chaos offered the first glimpses of an underlying architecture, though what principles governed it remained elusive. Every data point collected, every fluctuation measured, drew scientists closer to understanding and yet simultaneously highlighted the limits of current theory. In those oscillations, rotations, and spectral signatures lay the silent testimony of a cosmic narrative waiting to be deciphered, a story of motion, energy, and perhaps unknown cosmic laws quietly unfolding in the void. The situation escalated as 3I Atlas began to accelerate in ways that confounded even the most sophisticated orbital models. Observatories tracking the object noted deviations from predicted paths, small at first but growing increasingly pronounced as the days progressed. Gravity alone could not account for these shifts. Solar radiation pressure offered partial explanations, yet the magnitude and timing of the accelerations suggested additional forces at work, forces not accounted for in standard models of interstellar objects. The object's hyperbolic trajectory, initially a hallmark of its interstellar origin, now seemed to be supplemented by mechanisms that eluded conventional physics, propelling it unpredictably across the inner solar system. The acceleration manifested in multiple forms. Short bursts were observed in which the object gained velocity rapidly, followed by periods of relative calm, only to resume its erratic pace. These bursts did not correspond neatly with perihelion passage, nor with changes in solar radiation or nearby planetary influence. Such behavior sparked urgent modeling efforts, with teams worldwide attempting to simulate potential propulsion sources, internal or external, that could account for these movements. Outgassing, a common explanation for cometary acceleration, proved insufficient. No volatile emissions of the necessary magnitude were detected, and spectral analysis revealed no strong evidence of sublimation-driven thrust. The object seemed to defy traditional cometary dynamics, moving as if guided by unseen principles. Researchers explored alternative hypotheses, considering the possibility of interactions with interstellar magnetic fields. Charged particles on the surface could respond to these fields, producing subtle propulsion effects. Yet preliminary calculations suggested that the observed acceleration was orders of magnitude higher than any feasible electromagnetic influence. Others considered hypothetical microthrust phenomena, natural or artificial, that might intermittently energize the body. These speculations, while daring, underscored the profound uncertainty facing astronomers. Conventional mechanisms were failing to fully describe what was happening. Every model ran into limits, revealing the object as a living paradox within the equations of motion. The temporal pattern of acceleration added further intrigue. It was neither constant nor predictable, but exhibited faint signs of quasi-periodicity. Observers wondered whether the irregularities were the result of internal structural dynamics, perhaps uneven mass distribution or shifting material within the object, or if they were responses to some external stimulus, cosmic in origin. This ambiguity deepened the mystery, transforming the object from a mere astronomical curiosity into a challenge to fundamental assumptions about interstellar dynamics. If an object could accelerate without clear cause, what did this imply about the limits of known physics, and what hidden processes might exist in the interstellar medium? Emotionally, the acceleration of 3I Atlas heightened the tension for both scientists and the public. Enthusiasm mingled with apprehension as models predicting future trajectories could no longer provide certainty. Forecasts were issued with caveats, observations became more frequent, and every new data point was scrutinized for hidden patterns or explanatory anomalies. The object had moved beyond the status of a visitor. It now represented an active enigma, challenging observational prowess, theoretical frameworks, and even philosophical perspectives on cosmic order. Humanity was witnessing a celestial interloper whose motion was both scientifically perplexing and existentially humbling, a reminder that the universe does not yield its secrets easily, and that even distant, seemingly inert bodies can behave in ways that compel awe and wonder. The implications of this unexpected acceleration extended beyond pure mechanics. Scientists speculated that, if understood, 3I Atlas might reveal previously unrecognized forces or interactions within the cosmos, offering a glimpse into phenomena occurring in the interstellar medium, perhaps even hinting at unknown principles of matter, energy, or motion. This escalation in behavior marked a turning point in the observation campaign. The object was no longer just a point of light to be catalogued, but a dynamic, complex presence demanding the full attention of the global scientific community. Its every movement was a question written across the fabric of space, challenging humanity to decode, interpret, and ultimately to marvel at the depth of mystery residing in the interstellar void. As telescopes across the globe focused on 3I Atlas, optical observations revealed a series of extraordinary phenomena that further deepened the mystery. Sudden spikes in brightness punctuated the object's otherwise faint silhouette, sometimes doubling its luminosity within hours, only to fade again almost as quickly. These photometric surges did not correspond with rotation alone. The timing and intensity suggested active processes on or near the surface. Astronomers described these events with terms usually reserved for stellar phenomena: flaring, pulsing, and transient luminescence, creating a sense that the object itself was emitting signals, or at least interacting dynamically with ambient cosmic radiation in ways unseen in prior interstellar encounters. High-resolution imaging, though limited by distance and resolution, revealed subtle surface irregularities. The brightness oscillations hinted at uneven reflective regions, possibly composed of different materials, each responding uniquely to sunlight and cosmic radiation. Infrared and ultraviolet spectra showed corresponding variations, reinforcing the notion that the object's surface was heterogeneous and active. These optical oddities challenged the assumption that interstellar objects are inert chunks of rock or ice. Instead, 3I Atlas presented itself as a composite, dynamically engaging with its environment, with reflective patches that seemed almost deliberate in their configuration, though natural processes could not be ruled out. One particularly striking feature was the anisotropic reflection. Certain regions consistently reflected light at angles that others did not, producing directional flashes observable from Earth-based telescopes. This created a shimmering effect, as if the object were rotating unevenly or possessing facets that scattered light in unpredictable ways. For researchers, this phenomenon demanded consideration of both physical composition and geometrical shape. Was 3I Atlas elongated or irregularly shaped, like a needle, as some early models suggested, or did its surface properties account for the unusual optical behavior? Each scenario carried profound implications for understanding the forces and materials at play. Spectroscopy added another layer to the optical puzzle. Variations in spectral lines suggested transient emissions, hinting at energetic processes either on the surface or in the immediate vicinity. While comets can produce emission lines through outgassing, the spectral signatures observed here were inconsistent with typical volatiles like water, carbon monoxide, or methane. Some lines hinted at more exotic compounds, or even energetic interactions with cosmic rays, yet the data remained ambiguous. The combination of brightness, spikes, anisotropic reflection, and spectral anomalies painted a portrait of an object that seemed to exist in a state of constant flux, engaging in a subtle dialogue with the surrounding cosmic environment. The scientific community responded with heightened scrutiny. Observatories coordinated global monitoring campaigns, employing photometry, spectroscopy, polarimetry, and radar whenever feasible. Instruments tuned to different wavelengths sought correlations between brightness fluctuations and other environmental factors, such as solar wind or electromagnetic fields. Yet despite extensive observation, the optical oddities resisted simple explanation, reinforcing the perception that 3I Atlas was a wholly novel entity. It was not merely an interstellar visitor, it was an active participant in the interplay of light, motion, and energy, a phenomenon that simultaneously challenged expectations and inspired awe. Public fascination paralleled scientific intrigue. Astronomers shared images and time-lapse sequences, revealing the object's shimmer and pulsing light to a world captivated by its mysterious dance. Observers spoke of a celestial ballet, where the choreography was dictated not by human understanding, but by the subtle laws of a universe only partially known. Each optical anomaly became a reminder that, while the vast expanse of space can appear still and silent, it is also alive with motion, energy, and secrets, waiting for those attentive enough to perceive them. Through light alone, 3I Atlas had begun to tell a story, one of motion, transformation, and the persistent challenge of comprehending a cosmos that continually defies expectation. Amid the growing optical mysteries, gravitational analysis introduced an equally perplexing layer. The path of 3I Atlas, though broadly predictable under Newtonian and relativistic models, revealed subtle deviations that could not be explained by the positions or masses of known planets, moons, or minor bodies. Precision tracking indicated that its trajectory occasionally curved slightly, as if responding to a force that was invisible yet tangible in its effects. These discrepancies, though small in absolute terms, were highly significant in celestial mechanics. The slightest misalignment could ripple through predictive models, challenging the core assumptions of how interstellar bodies interact with gravitational fields across space. Attempts to account for these deviations prompted meticulous simulations. Astronomers applied n-body calculations, factoring in every major planetary mass, the Sun's gravitational influence, and even tidal effects from distant dwarf planets. Yet, even the most sophisticated models failed to reproduce the subtle oscillations in velocity and direction. The object appeared to dance along an invisible line, occasionally accelerated, occasionally slowed, responding to parameters unknown. Some hypothesized that gravitational lensing or passing interstellar masses might exert influence, yet surveys of nearby stars and molecular clouds revealed nothing sufficient to explain the observed motion. The object seemed to occupy a liminal space where conventional physics strained to maintain coherence. Further complicating the picture were minute interactions with the interstellar medium. 3. I-Atlas traversed regions of variable density, encountering clouds of gas and dust that, in principle, could impart small forces. Yet calculations indicated that these interactions were far too weak to produce the deviations recorded. Magnetic fields likewise were considered. Charged particles on the object's surface could experience Lorentz forces, subtly nudging its course. But even under generous assumptions about charge accumulation and field strength, the anomalies persisted beyond reasonable explanation. Each new gravitational inconsistency deepened the sense of an unknown influence at work, an invisible hand-shaping motion in ways science had not yet encountered. The gravitational puzzle became a central focus for international collaboration. Observatories across multiple continents synchronized their measurements, refining orbital parameters daily. Small discrepancies between datasets became crucial. A millisecond timing error or arc-second misalignment could distinguish between known physics and the onset of truly anomalous behavior. Teams cross-checked their methods, recalibrated instruments, and reanalyzed historical data for overlooked patterns. The result was a meticulous tapestry of observations revealing an interstellar visitor that consistently defied expectations, forcing astronomers to confront the possibility that unknown forces or phenomena might subtly govern its motion. Philosophically, the gravitational anomalies carried profound implications. Humanity, accustomed to a universe bound by predictable laws and elegant equations, faced an object whose very existence seemed to bend those rules. The trajectory of 3I, Atlas, became a mirror for our understanding of the cosmos, reflecting both the limits of knowledge and the tantalizing suggestion that interstellar space is not merely empty, but filled with subtle currents and influences yet to be catalogued. Scientists remarked on the elegance of the anomalies themselves. Within the apparent chaos, patterns emerged, suggesting a hidden order that beckoned exploration, modeling, and reflection. In the public sphere, these gravitational oddities captivated attention as much as the visual spectacle. Reports highlighted the object's unexplained turns and erratic dance, bringing lay audiences closer to the scientific drama unfolding millions of kilometers away. This interplay of motion and mystery, grounded in precise measurement yet seemingly defying comprehension, transformed 3I Atlas from a distant astronomical curiosity into a narrative of cosmic significance. It was an encounter that tested the precision of human instruments, the rigor of mathematical modeling, and the humility of those who sought to understand the silent forces at work in the vast interstellar void. Spectral observations added yet another layer of intrigue to the evolving portrait of 3I Atlas. Astronomers pointed high-resolution spectrometers at the object, capturing light across a broad swath of wavelengths from ultraviolet to infrared to discern its composition and energetic behavior. The results were startling. The spectra exhibited lines and absorption features inconsistent with typical interstellar or solar system bodies. Some peaks suggested exotic ices and organic compounds rarely observed outside dense molecular clouds, while others hinted at energetic emissions perhaps caused by cosmic ray interactions or transient surface phenomena. No single explanation fully reconciled the data, deepening the mystery and suggesting that the object's very makeup might be as unusual as its trajectory. One of the most compelling spectral anomalies was the presence of transient emission lines in the ultraviolet. These brief flashes indicated bursts of energy, appearing and disappearing on timescales of hours. While comets occasionally exhibit emissions due to outgassing, the patterns observed in 3I Atlas did not align with known volatile behaviors. There was no corresponding evidence of large-scale sublimation or visible cometary tails, yet the energetic spikes persisted. The data suggested localized, intermittent processes at work on or near the surface processes that could involve molecular rearrangements, electrical discharge phenomena, or interactions with charged particles in the surrounding interstellar medium. Infrared spectra revealed similarly perplexing features. Certain absorption bands suggested compounds rich in carbon and nitrogen, yet in proportions not typically seen in either comets or asteroids. These spectral signatures were stable over multiple observations, indicating that the anomalous composition was intrinsic to the object rather than a transient contamination from passing dust clouds. Additionally, variations in infrared emission corresponded subtly with periods of optical brightness changes, implying a coupling between surface composition and the reflective phenomena observed earlier. This correlation hinted at an interconnected system of physical processes governing the object's appearance, composition, and perhaps even its motion. The combination of optical and spectral anomalies challenged existing models of interstellar bodies. Scientists considered numerous explanations. Could the object be coated with exotic crystalline ices that reflect and emit light in unpredictable ways? Might it contain high-energy minerals or metallic compounds capable of producing the observed emissions under solar irradiation? Or, more speculatively, could the object's surface be engineered in some fashion, a vestige of intelligent design, leaving detectable signatures in both reflection and emission? While such notions were speculative, the data refused to conform to simple natural explanations, prompting researchers to maintain openness to unconventional possibilities, constrained always by empirical rigor. The spectral investigations also carried philosophical weight. By revealing material signatures from a region of space far beyond the solar system, 3I Atlas acted as an emissary of the interstellar medium, offering direct insights into the chemical diversity and energetic processes of distant stellar neighborhoods. Each spectral anomaly was a note in a silent symphony, hinting at the complexity of the universe and the subtle forces that shape it. Scientists marveled at the richness encoded in light alone, recognizing that even a small object traversing space at incredible speed could carry with it stories of distant star systems, cosmic history, and the dynamic interplay of matter and energy across unimaginable distances. Through repeated observation and careful analysis, the emerging picture of 3I Atlas became one of layered complexity. Its optical oddities and spectral signatures together suggested that this object was not merely inert, but a dynamic participant in the cosmic environment, interacting with radiation, particles, and perhaps fields in ways that challenged established understanding. By scrutinizing these features, humanity glimpsed processes occurring in deep space that had hitherto been theoretical or entirely unobserved, underscoring the object's unique role as a bridge between empirical measurement and the unknown mysteries of interstellar physics. The more closely it was observed, the more 3I Atlas revealed both its tangible presence and the limits of human comprehension. With data accumulating from multiple wavelengths and instruments, scientists began exploring the possibility that 3I Atlas's peculiar behavior could be the result of collisions or interactions with other cosmic matter. Initial hypotheses considered impacts with tiny interstellar debris, micrometeoroids, and dust particles that pervade the void between stars. Even at high relative velocities, such collisions were expected to produce only minor alterations to trajectory or surface properties. Yet, the observed changes in motion and brightness appeared too substantial to be explained solely by these minor impacts. It became increasingly clear that conventional impact models, long used to describe the evolution of asteroids and comets, were insufficient to account for the data, leaving researchers grappling with the inadequacy of established explanations. Solar flares and space weather phenomena were also evaluated as potential influences. Could sudden bursts of solar wind or coronal mass ejections impart sufficient force to cause the irregular accelerations and reflective anomalies observed? Calculations showed that while solar events can affect small bodies, the magnitude and timing of the accelerations in 3I Atlas were inconsistent with such transient forces. Some velocity shifts occurred in regions of space where the influence of the Sun's activity should have been minimal, reinforcing the notion that the forces at work were either internal, cosmic in origin, or indicative of a previously unrecognized mechanism. The object seemed to respond to conditions in ways that defied simple causation, prompting continued debate among theorists. Particle interactions presented another avenue of investigation. Cosmic rays, interstellar plasma, and magnetic fields can exert subtle forces on charged or partially ionized objects, potentially influencing rotation or trajectory over time. Yet, even sophisticated simulations incorporating interstellar field strengths and particle fluxes failed to replicate the observed dynamics fully. The coupling between surface properties, ambient particles, and electromagnetic effects remained poorly constrained, highlighting a gap in current understanding. Researchers began to realize that 3I Atlas was operating at the edge of observable physics, a case study in complexity that could illuminate phenomena hidden in more mundane celestial bodies. Another line of inquiry considered near-miss gravitational interactions with as yet undetected minor bodies or rogue planetary remnants. Could a passing substellar object have imparted subtle nudges, temporarily altering its path? Surveys and deep space scans found no evidence for such encounters, narrowing the range of feasible explanations. The combination of acceleration, optical irregularities, and spectral anomalies suggested that the behavior was intrinsic to the object itself or resulting from a set of influences not yet identified. In other words, the object's chaos was not easily reducible to external impacts or standard cosmic interactions. Despite these attempts, the puzzle persisted. Every proposed mechanism offered partial explanations, yet none could account for the full array of phenomena. Collisions, solar activity, and particle interactions each left critical gaps in the model. Scientists began acknowledging that 3I Atlas represented a unique natural laboratory, a singular opportunity to probe behaviors and forces that rarely manifest in observable interstellar objects. Its anomalies invited a re-evaluation of theoretical frameworks, forcing the astrophysics community to consider mechanisms previously relegated to speculation or theory. This realization transformed the investigation. The objective was no longer simply to describe motion or composition, but to probe the frontier of what was scientifically conceivable. By the close of this phase, it was evident that 3I Atlas had escalated from a curious interstellar visitor to a profound challenge to comprehension. Its collisions, or apparent lack thereof, and its anomalous behaviors underscored the inadequacy of conventional explanatory models, pushing scientists toward more creative and speculative avenues of inquiry. What had begun as a routine detection had matured into an event that demanded interdisciplinary analysis, the pooling of global resources, and, perhaps most importantly, humility. The object had become an emblem of cosmic complexity, a reminder that even small points of matter, traveling silently through the void, could reveal the deep, uncharted structures of reality. As the volume of observational data grew, the deeper investigation into 3I Atlas revealed layers of complexity that were previously invisible. Coordinated monitoring campaigns brought together optical, infrared, ultraviolet, and radar observations, producing a multi-dimensional portrait of the object. Patterns once obscured by the noise of initial measurements began to crystallize. Subtle periodicities in brightness, shifts in spectral lines, and minor deviations in trajectory suggested that the object was governed by a combination of factors, some known, others entirely unexpected. The integration of these diverse datasets allowed astronomers to detect correlations that had been invisible in isolated observations, hinting at the sophisticated interplay of forces shaping the object's behavior. One emergent pattern was the quasi-periodic modulation of brightness, which appeared to synchronize weakly with changes in spectral emissions. Researchers hypothesized that this might be evidence of surface heterogeneity, possibly alternating regions of reflective and absorptive materials responding to solar illumination. Alternatively, the variations could indicate transient energetic processes, perhaps driven by the interaction of 3I Atlas with charged particles or micromagnetic fields within its vicinity. Each scenario carried profound implications. If surface composition alone drove the effects, the object represented a unique geological specimen. If energetic processes were responsible, it could suggest dynamics operating at levels not yet understood in interstellar objects. Radar observations, though limited by distance and size, provided additional insight into shape and rotation. Echo patterns indicated that 3I Atlas might be elongated or irregularly structured, contributing to the observed optical and spectral anomalies. The rotations inferred from these radar profiles were non-uniform, exhibiting intermittent accelerations and decelerations, further complicating the analysis. Such irregular motion defied standard rotational models for small celestial bodies, challenging the assumption that interstellar visitors behave as simple tumbling solids. The radar data reinforced the emerging picture of a dynamic, multifaceted object with behavior shaped by both intrinsic properties and external interactions. High-resolution spectroscopic monitoring revealed subtle shifts in elemental signatures over time. Certain absorption features appeared and disappeared, while emission lines fluctuated in intensity, suggesting that the surface or immediate environment was changing dynamically. These changes could be driven by localized heating, chemical reactions, or interactions with interstellar radiation, yet none of the proposed mechanisms fully accounted for the breadth of anomalies. Researchers debated whether these spectral shifts were evidence of processes occurring on the object itself, or indications of interactions with an unseen cosmic environment, such as variable interstellar magnetic fields or particle streams. The data painted a picture of a system in constant, subtle flux, resistant to straightforward categorization. The deeper investigation also underscored the importance of temporal resolution in understanding 3I Atlas. Continuous monitoring over extended periods revealed that many of the anomalies were transient, appearing in bursts rather than as continuous phenomena. These temporal patterns were critical for developing models that could account for both periodic and stochastic behaviors. By cross-referencing data from multiple observatories and instruments, scientists were able to construct a composite timeline of events, revealing correlations between light curves, spectral shifts, and trajectory deviations. This multi-layered approach illuminated the interconnectedness of the object's properties, suggesting that optical, spectral, and dynamical anomalies were not independent, but part of a complex systemic behavior. By the conclusion of this investigative phase, 3I Atlas had emerged as far more than an interstellar visitor. It was a locus of scientific inquiry that challenged instrumentation, methodology, and theory simultaneously. Each layer of data, optical, radar, spectral, and dynamical, added depth to the enigma, revealing a sophisticated choreography of forces and interactions. Scientists now faced the dual task of interpreting these patterns and integrating them into a coherent model, aware that every proposed explanation would need to reconcile multiple, sometimes contradictory, observational dimensions. In doing so, 3I Atlas was not only expanding human knowledge, but also redefining the boundaries of what could be understood about interstellar objects and the subtle physics governing their journey through the void. As 3I Atlas continued its voyage through interstellar space, an unexpected revelation emerged. The object exhibited measurable magnetic disturbances, subtle yet persistent anomalies in the surrounding magnetic field detected by sensitive instruments. Observatories equipped with magnetometers and space-based probes reported deviations that seemed to correlate with the object's passage, suggesting that 3I Atlas was interacting actively with cosmic magnetic fields. These signatures were neither static nor uniform. They fluctuated in intensity and orientation, implying dynamic interactions rather than a simple passive response to ambient conditions. For astrophysicists, this represented a profound puzzle, one that blended dynamics, composition, and electromagnetic theory into a single, intractable mystery. The magnetic anomalies posed immediate questions regarding the object's intrinsic properties. Was 3I Atlas itself magnetized, possessing regions of ferromagnetic material aligned in complex configurations? Or were the effects entirely external, produced by the interaction of a conductive or charged surface with interstellar magnetic fields? Observations suggested that neither explanation alone sufficed. The magnitude and variability of the disturbances implied a coupling between intrinsic and environmental factors, a phenomenon rarely observed in small interstellar bodies. The data hinted at a deeper, perhaps hidden structure within the object, one capable of generating or modulating electromagnetic fields in concert with motion and orientation. Researchers proposed several mechanisms for these magnetic phenomena. One hypothesis considered the influence of charged dust or plasma envelopes surrounding the object, interacting with local interstellar currents to produce transient magnetic signatures. Another posited the presence of ferrous inclusions within the object, responding dynamically to both rotational motion and external fields. Yet each explanation faced challenges in fully replicating the observed oscillations and intensity patterns. Computational simulations, run on supercomputing clusters, attempted to model these interactions across multiple variables: composition, rotation, velocity, and field strength. But even the most sophisticated simulations could not reproduce the full complexity of the anomalies. In essence, 3I Atlas appeared to be playing by rules that straddled the boundary between known physics and uncharted phenomena. The implications extended beyond theoretical curiosity. Magnetic interactions influence trajectory subtly, particularly over long distances, potentially accounting for some of the small, unexplained accelerations noted earlier. If 3I Atlas carried a magnetic field of its own, interacting with interstellar currents, it could provide a natural explanation for at least part of the erratic motion. Yet this alone did not account for optical and spectral anomalies, indicating that magnetic properties were one component in a multifaceted system of interactions. Researchers realized that to fully understand the object, they would need to integrate magnetic, optical, and dynamical data into a coherent, multi-dimensional model, a task both complex and unprecedented. Philosophically, the presence of magnetic disturbances lent 3I Atlas an almost living quality, not in consciousness, but in responsiveness. The object's motion and properties appeared to engage with its environment, creating a feedback loop in which interactions altered subsequent behavior. Such phenomena challenged traditional conceptions of interstellar bodies as inert and predictable. For humanity observing from millions of kilometers away, the effect was both humbling and exhilarating. The universe, it seemed, had more subtlety and agency than previously appreciated. Even in the void, forces of invisible power could shape motion and energy in ways that demanded awe and careful attention. The discovery of magnetic interactions intensified observational campaigns. Space agencies recalibrated magnetometers and coordinated cross-instrument measurements to determine whether the anomalies were local to 3I Atlas or influenced by broader interstellar structures. By comparing readings from distant observatories and satellites, scientists sought to triangulate the source and characteristics of the fields. Each observation reinforced the enigmatic character of the object. It was not only an interstellar visitor in motion, but a dynamic participant in the magnetic tapestry of the galaxy. Through these disturbances, 3I Atlas quietly announced itself as a phenomenon bridging the observable and the enigmatic, demanding a synthesis of physics, observation, and imagination to begin to grasp its full nature. As the magnetic anomalies gained attention, theorists turned their focus toward understanding the mechanisms behind 3I Atlas's erratic acceleration. Classical explanations, gravitational perturbations, radiation pressure, minor collisions had proven insufficient. The object's movement appeared to involve forces either internal or coupled to its surrounding environment in ways that resisted direct measurement. Researchers began exploring the possibility of microthrust phenomena, subtle, intermittent accelerations generated by processes small in scale but cumulative in effect, capable of producing the observed trajectory deviations without the need for cataclysmic events. These microthrusts could arise from uneven mass distribution, sublimation of exotic volatiles, or even interactions with charged particles in the interstellar medium. Outgassing, the conventional explanation for cometary acceleration, was scrutinized in meticulous detail. Spectroscopic analysis had revealed minimal signs of typical cometary volatiles such as water, CO, or methane, but did not exclude the presence of less common or complex molecules capable of producing subtle thrust. Researchers modeled hypothetical jets emerging from specific regions of the surface, taking into account shape, spin, and orientation relative to solar radiation. These simulations demonstrated that, in principle, small but persistent emissions could generate measurable accelerations over the course of days or weeks. Yet the magnitude and pattern of 3I Atlas's changes often exceeded these models, implying additional factors were at play. Another hypothesis considered electromagnetic forces acting on a charged or conductive surface. As 3I Atlas traversed interstellar plasma and solar wind environments, differential charging could produce Lorentz forces, inducing rotational and translational changes. In combination with surface irregularities and anisotropic reflection, such forces could contribute to the observed optical and dynamic anomalies. Computational models indicated that while electromagnetic interactions could explain some periodic deviations, they could not fully account for the magnitude or timing of all observed accelerations. Consequently, scientists were compelled to consider multifactorial explanations, where several mechanisms combined in complex ways to influence the object's behavior. Historical comparisons proved invaluable. the previous interstellar visitor, Oumuamua, exhibited unexplained acceleration that prompted debates over natural versus artificial causes. In contrast, 3I Atlas presented a richer dataset, including magnetic signatures, spectral anomalies, and optical fluctuations, allowing theorists to refine models and test hypotheses more rigorously. Lessons learned from prior events informed the parameters used in simulations, yet 3I Atlas consistently revealed behaviors exceeding those expectations, suggesting either a natural phenomenon of unprecedented complexity or the influence of forces not yet fully understood. The investigation extended into speculative territory, guided by rigorous scientific reasoning. Could the object possess an internal structure capable of generating directional thrust? Might localized chemical or energetic reactions subtly alter momentum? While these ideas pushed the bounds of established astrophysics, they remained grounded in empirically measurable effects, constrained by the laws of conservation of energy and momentum. Simultaneously, researchers remained cautious, resisting the temptation to invoke unverified phenomena without observational support, even as the data challenged conventional understanding. The implications of these acceleration mechanisms were profound. If validated, they could expand knowledge of interstellar object dynamics, revealing subtle interactions previously undetectable with existing technology. Moreover, understanding these forces might offer insights into the evolution, composition, and long-term behavior of objects traversing the interstellar medium. For humanity, the combination of acceleration, magnetic interactions, and surface anomalies transformed 3I Atlas from a transient visitor into a natural laboratory, where every movement and fluctuation offered a lesson in the subtle physics of deep space, bridging observation, theory, and speculative exploration in a single, enigmatic phenomenon. In the course of analyzing 3I Atlas, scientists drew comparisons to Voyager's historic encounters with the outer planets, as well as the interstellar observations of Oumuamua, seeking patterns that might illuminate the object's enigmatic behavior. While both previous missions had provided invaluable insight into the mechanics of interstellar travel and observation, 3I Atlas presented a level of complexity unparalleled in modern astronomy. Unlike the controlled trajectories of Voyager or the brief, sparsely documented passage of Oumuamua, this object was simultaneously exhibiting rotational irregularities, spectral anomalies, optical oscillations, and subtle gravitational deviations. Historical parallels provided context, but also underscored the uniqueness of the current phenomenon. Researchers noted that Oumuamua's elongated shape, non-gravitational acceleration, and lack of visible coma had sparked debates about the possibility of artificial structures or unknown natural processes. 3I Atlas, in contrast, presented a broader array of observable data. Its magnetic signatures, transient spectral emissions, and quasi-periodic optical behavior suggested that a richer and more complex set of interactions was in play. The comparison illuminated both the progress in observational capabilities and the persistent limits of understanding. Just as Oumuamua had challenged assumptions about the frequency and nature of interstellar visitors, 3I Atlas was testing the bounds of knowledge, compelling astronomers to reconcile observational sophistication with theoretical flexibility. Historical context also highlighted the evolution of instrumentation and methodology. The detection of Oumuamua relied primarily on optical surveys and limited follow-up, while 3I Atlas benefited from coordinated global campaigns, multi-wavelength observations, and real-time data sharing. This enabled scientists to observe subtle dynamics that would have been invisible in earlier decades. revealing complex behaviors that suggested more intricate internal structures or external interactions. By comparing these datasets, researchers could begin to isolate which phenomena were unique to 3I Atlas and which might reflect broader properties of interstellar objects, refining theoretical models and enhancing predictive capability. The comparison also reinforced the importance of caution in interpretation. Oumuamua's anomalous acceleration had been debated extensively, with explanations ranging from outgassing of exotic ices to the provocative suggestion of an engineered structure. In studying 3I Atlas, scientists were mindful of the tendency to leap to extraordinary conclusions without sufficient empirical evidence. While some features hinted at mechanisms beyond conventional understanding, researchers emphasized that speculative hypotheses must be rigorously tested against observable data. The historical precedent of Oumuamua served as both inspiration and a cautionary tale, to explore boldly, yet anchor theories firmly in measurement. From a philosophical perspective, these comparisons underscored humanity's ongoing dialogue with the cosmos. Interstellar visitors, rare and fleeting, act as emissaries of distant regions, carrying within them the chemical, physical, and dynamical histories of other stellar neighborhoods. Each encounter provides a mirror, reflecting the limits of knowledge and the possibilities of discovery. By situating 3I Atlas within this continuum, scientists could appreciate both its novelty and its broader significance, recognizing the object as a participant in a lineage of interstellar phenomena that challenge assumptions and expand cosmic awareness. The lessons gleaned from Voyager and Oumuamua also shaped public and scientific perception of 3I Atlas, communicating the nuances of comparison, highlighting both similarities and unprecedented differences, helped convey the extraordinary nature of the observations without resorting to hyperbole. This balance between historical context and emergent discovery emphasized the object's unique role in advancing knowledge, a singular interstellar visitor whose behaviors, once contextualized, offered an evolving framework for understanding both familiar physics and the potential for new, uncharted phenomena in the universe. As the object's anomalies became increasingly pronounced, some researchers began contemplating speculative propulsion mechanisms, raising questions that teetered on the boundary between natural and artificial. The behavior of 3I Atlas, its erratic accelerations, optical oscillations, and spectral irregularities resisted explanation through conventional processes alone. While outgassing, magnetic interactions, and gravitational influences could account for certain aspects of its motion, the cumulative patterns suggested the possibility of directed forces or mechanisms unknown in natural interstellar bodies. These hypotheses were treated cautiously, always grounded in physical plausibility, yet they opened the door to a broader discussion. Could 3I Atlas possess features or internal processes capable of generating controlled motion? The speculative propulsion models explored a range of natural phenomena that might produce directed acceleration. One consideration was the uneven release of volatile materials across the surface, effectively producing a series of microjets. While previously examined, the spatial and temporal distribution of these emissions remained difficult to reconcile with the observed erratic trajectory. Another hypothesis posited the influence of electromagnetic forces acting in concert with rotational asymmetries, allowing the object to harness ambient magnetic fields as a subtle, natural thrust. Each model required precise conditions, often improbable, yet the data suggested that some combination of processes could be at work. Parallel to natural explanations, more provocative ideas emerged. Could the object harbor structures or materials arranged to produce directed motion akin to a rudimentary or engineered propulsion system? While such considerations edged toward artificiality, scientists emphasized that speculative reasoning remained a legitimate tool when constrained by observable phenomena and fundamental physics. Unlike conjecture divorced from measurement, these models relied on the empirical data, velocity deviations, magnetic interactions, and optical anomalies, all of which demanded explanation. The discussion was framed carefully, balancing curiosity with scientific rigor, acknowledging that extraordinary claims required extraordinary evidence. The prospect of such propulsion mechanisms intersected with ongoing debates about the diversity of interstellar objects. Perhaps 3I Atlas represented a class of bodies previously undetected, natural in origin yet possessing dynamic behaviors rarely observed. Some theorists suggested that objects traveling between stars over millions of years could accumulate unusual surface charges or layered compositions capable of producing intermittent acceleration through mechanisms not typically present in solar system asteroids or comets. This view preserved the object's natural origin while offering a framework for explaining its unusual behaviors without invoking intelligence. Importantly, these discussions were not purely theoretical. Computational simulations tested various configurations of shape, composition, rotation, and environmental interaction, attempting to reproduce the observed accelerations and optical signatures. By adjusting variables such as surface conductivity, mass distribution, and exposure to cosmic particle flux, researchers explored a range of plausible models. While no single model fully captured the complexity of the observations, these exercises illuminated which mechanisms could contribute significantly to the object's motion, helping refine understanding and prioritize further observations. Philosophically, the consideration of speculative propulsion reflected humanity's grappling with the limits of knowledge. Even as astronomers sought natural explanations, the mere possibility of directed mechanisms challenged assumptions about interstellar physics, object behavior, and the nature of cosmic rarity. 3I Atlas had become not merely an object to study, but a stimulus for inquiry, a prompt to question the assumptions underlying celestial mechanics, to explore the interplay of observation and speculation, and to acknowledge that the universe might harbor processes or structures beyond current comprehension. In its silent journey through the void, the object invited reflection, pushing both theory and imagination to the edges of what was known and what might be possible. As observations progressed, researchers began exploring quantum-scale phenomena as potential contributors to 3I Atlas's enigmatic behavior. While classical mechanics accounted for much of celestial motion, subtle irregularities in the object's trajectory and surface interactions prompted consideration of effects operating at the subatomic level. Could interactions with dark matter, quantum fluctuations, or other exotic particles be influencing its path? Although speculative, these ideas were grounded in established physics. Quantum mechanics predicts fluctuations and field interactions that, while minuscule individually, could produce measurable effects over long distances or under specific interstellar conditions. 3I Atlas presented a rare opportunity to probe these subtle influences on a macroscopic scale. One area of focus was the possibility of quantum vacuum effects. In regions of low particle density, fluctuations in the vacuum's energy could, in theory, impart tiny random forces on small bodies. While such forces are typically negligible, their cumulative influence across millions of kilometers of interstellar travel could produce detectable anomalies in velocity or rotation. Scientists employed simulations to estimate the magnitude of such effects, comparing predictions with the observed accelerations and deviations. The results were intriguing. While quantum vacuum forces alone could not account for all anomalies, they could conceivably contribute to the complex interplay of influences shaping 3I Atlas's behavior. Another avenue considered interactions with dark matter. Interstellar space, while largely empty, contains a pervasive sea of unseen mass, detectable only through gravitational effects. Could high-velocity passage through denser regions of dark matter produce subtle perturbations in the object's trajectory? Modeling these interactions required assumptions about particle density, distribution, and the object's cross-sectional characteristics. Preliminary estimates suggested the effect would be extremely weak, yet when combined with other forces, magnetic, electromagnetic, and surface-driven accelerations, the contribution could help explain minor irregularities that previously resisted explanation. This approach integrated macroscopic observation with microscopic physics, bridging scales in a novel and compelling way. Researchers also examined quantum-level interactions in the context of surface phenomena. Could photon absorption, emission, or scattering at the atomic level induce minute rotational torques or shifts in reflective properties? Spectral data hinted at interactions between incident solar radiation and complex surface materials that might produce subtle, fluctuating forces. While these effects were marginal in isolation, they offered a potential explanation for the quasi-periodic brightness variations and intermittent emissions noted in previous sections. Quantum considerations thus provided an additional layer of understanding, highlighting the interplay between fundamental physics and observed anomalies. The exploration of quantum shadows extended beyond mechanics into philosophical reflection. The object's behavior suggested that even in the macroscopic world of interstellar travel, phenomena rooted in the quantum fabric of reality could leave measurable fingerprints. It blurred the traditional distinction between microscopic unpredictability and the deterministic celestial motions studied for centuries. In observing 3I Atlas, scientists were, in a sense, witnessing the influence of the universe's most fundamental laws manifest in a tangible, observable form, a rare convergence of theory and empirical reality. Ultimately, considering quantum-scale effects underscored the richness and complexity of 3I Atlas. No single mechanism, classical or quantum, could fully account for its behavior. Instead, the object emerged as a nexus of forces, from gravitational and magnetic to quantum and speculative, interacting in subtle and sometimes counterintuitive ways. In this convergence, humanity glimpsed both the power and the limits of scientific understanding, a reminder that the universe, in all its vastness, is governed by layers of reality that interconnect in ways both observable and mysterious, with 3I Atlas serving as an eloquent, traveling testament to that intricate tapestry. The passage of 3I Atlas through the solar system presented a natural laboratory for testing the predictions of Einstein's general relativity under conditions rarely encountered by human observation. While Newtonian mechanics provided a first-order approximation of its motion, subtle deviations prompted careful consideration of relativistic effects. The object's high velocity and hyperbolic trajectory meant that time dilation, gravitational lensing, and frame dragging, though small, could influence observational measurements. By precisely accounting for these relativistic factors, astronomers aimed to refine their models and determine whether the anomalies could be reconciled with known physics or pointed toward previously unobserved phenomena. One key area of focus was the effect of the Sun's gravitational curvature on the object's trajectory. According to general relativity, massive bodies distort space-time, altering the paths of nearby objects and the propagation of light. Calculations incorporating the Sun's influence allowed researchers to correct for slight deviations in 3I Atlas's apparent path, separating relativistic effects from other sources of acceleration. Even after accounting for these factors, however, the object's motion continued to defy complete explanation, suggesting that additional forces or interactions, perhaps magnetic, electromagnetic, or quantum in nature, remained at work. Gravitational lensing also played a role in observational interpretation. Light from 3I Atlas, passing near massive bodies or dense regions of space, experienced slight bending, subtly affecting measurements of position and brightness. While the lensing effects were minimal, they were detectable with high-precision instrumentation, requiring careful modeling to avoid misattributing these optical artifacts to intrinsic properties of the object. By incorporating relativistic corrections, scientists improved the accuracy of their trajectory predictions and clarified the true nature of optical anomalies, though many questions persisted. Frame dragging, a relativistic effect caused by rotating massive bodies, offered another avenue of inquiry. Though primarily associated with rapidly spinning stars or black holes, its theoretical influence on interstellar objects was considered in simulations, especially when assessing the cumulative impact of multiple gravitational sources. These relativistic factors, though subtle, highlighted the necessity of precision in modeling 3I Atlas's motion, reinforcing the notion that even small corrections can be crucial when interpreting the dynamics of fast-moving interstellar visitors. Beyond technical corrections, the relativistic perspective provided deeper philosophical insight. Observing 3I Atlas under the lens of general relativity emphasized the interconnectedness of space, time, and motion. The object's path was not merely a line through emptiness, but a journey along the contours of space-time itself, influenced by mass, energy, and the subtle curvature of the cosmic fabric. Its motion offered a tangible demonstration of principles first articulated over a century ago, yet still profoundly relevant, bridging theory and observation in real time. In synthesizing relativistic considerations with observational data, astronomers gained both clarity and humility. Einstein's equations could account for certain deviations, refine models, and illuminate subtle effects, yet they could not explain all aspects of 3I Atlas's behavior. The integration of relativity with other mechanisms, magnetic, quantum, optical, revealed a layered reality in which multiple forces operate simultaneously, producing outcomes that challenge conventional expectation. In this framework, the object became not only a subject of empirical study, but a philosophical prompt, reminding humanity that even in the precise language of mathematics, the universe retains its capacity for surprise, wonder, and profound complexity. As 3I Atlas traversed deeper into the solar system, scientists began exploring the potential influence of dark energy on its motion, a consideration rarely applied to individual interstellar objects. Dark energy, the mysterious force driving the accelerated expansion of the universe, is typically observed only on cosmological scales, governing the behavior of galaxies separated by millions of light-years. Yet, given the object's peculiar acceleration and deviations from expected trajectories, some theorists posited that even subtle manifestations of dark energy might have detectable effects over vast interstellar distances, providing a conceptual framework for the anomalies that resisted conventional explanations. Calculations focused on the potential cumulative impact of dark energy's repulsive influence. While the effects on small bodies like 3I Atlas are expected to be vanishingly small, the precision of modern instrumentation allowed scientists to consider contributions at levels previously regarded as negligible. By integrating estimates of dark energy density into orbital models, researchers examined whether slight deviations in the object's velocity or trajectory could be partially attributable to this pervasive cosmic force. The results, though tentative, suggested that dark energy could contribute minutely to motion, perhaps interacting with other forces in ways that amplify observable anomalies. Simultaneously, the object's acceleration prompted a re-evaluation of cosmological assumptions on a local scale. Could interstellar objects, moving through regions of space with slightly varying dark energy density or encountering gravitational gradients, experience effects detectable within observational windows? Though speculative, this line of inquiry emphasized the need to bridge micro and macro perspectives, considering how forces usually confined to galactic scales might manifest subtly in local phenomena. By framing 380LAS's behavior in this broader cosmological context, researchers connected the immediate mystery to the underlying dynamics of the universe itself. Critically, these investigations reinforced the object's role as a probe into unseen phenomena. Whether or not dark energy significantly influenced 3I Atlas's motion, considering its potential effects expanded the boundaries of observational astrophysics. It encouraged scientists to model interstellar travel not only through classical mechanics and local forces, but also with an awareness of the subtle, pervasive influences that operate across the cosmic fabric. This integration of large-scale cosmological considerations with high-precision local observations exemplified the depth and sophistication of contemporary scientific inquiry. Philosophically, the potential influence of dark energy lent the object an almost poetic dimension. It became a messenger of the universe's grand-scale dynamics, linking the human-scale act of observation to forces that shape the cosmos on incomprehensible scales. In a sense, 3I Atlas was a conduit, allowing humanity to witness firsthand the delicate interplay of known and unknown forces, bridging empirical measurement and the profound mystery of universal expansion. Even if dark energy's role was subtle, its conceptual inclusion highlighted the object's capacity to illuminate both the local and the cosmic, deepening the resonance of its passage across the void. In considering dark energy alongside other mechanisms, magnetic interactions, quantum fluctuations, relativistic corrections, the object emerged as a nexus of forces operating at multiple scales. Each layer contributed to the cumulative behavior observed, creating a phenomenon simultaneously grounded in measurable physics and suggestive of deeper unknowns. The contemplation of dark energy's subtle effect underscored a broader principle. In the vastness of space, no force, however faint, is irrelevant, and even small interstellar travelers can become instruments for probing the fundamental nature of reality. As the mystery deepened, observational intensity reached its zenith. Space agencies and astronomical observatories worldwide coordinated unprecedented monitoring campaigns, deploying advanced instrumentation to capture every nuance of 3I Atlas's behavior. Optical telescopes tracked its reflective properties, while infrared and ultraviolet sensors recorded transient emissions. Polarimeters assessed light scattering, magnetometers measured fluctuating fields, and radar systems probed its shape and rotation. Even space-based instruments, often reserved for planetary or stellar observation, were tasked with capturing complementary data, ensuring that every dimension of the object's motion and energy was meticulously documented. The global effort transformed 3I Atlas from a distant anomaly into a collective scientific focus, uniting disciplines in pursuit of understanding. High-resolution spectroscopy became a critical tool. Observatories synchronized their observations to detect minute variations in elemental and molecular signatures across the object's surface. This allowed scientists to correlate transient spectral emissions with optical fluctuations, revealing subtle patterns in material distribution and energetic activity. Infrared sensors detected heat anomalies that suggested localized surface processes, possibly linked to microthrusts or electromagnetic interactions. Ultraviolet instruments recorded sporadic emissions, challenging researchers to model complex energy exchanges between 3I Atlas and its interstellar environment. The depth and breadth of these measurements provided an unprecedented multi-wavelength perspective, crucial for disentangling overlapping phenomena. Radar imaging contributed structural insights. By analyzing echoes reflected from the object's surface, researchers inferred irregular geometry, possible elongation, and rotational dynamics. These physical characteristics, combined with optical and spectral data, suggested that 3I Atlas was not a homogeneous, inert body, but a complex system interacting dynamically with its environment. Variations in rotation and reflective patterns pointed to uneven mass distribution or surface heterogeneity, while the temporal correlation with spectral anomalies implied that these features were not static, but actively evolving during its passage through the solar system. Space-based monitoring added further precision. Instruments aboard orbiting observatories and planetary probes provided continuous observation unaffected by atmospheric interference, capturing subtle luminosity changes and trajectory deviations otherwise difficult to detect from Earth. These data streams were integrated in real time with ground-based measurements, allowing for rapid updates to orbital models and anomaly detection. The combination of terrestrial and space-based resources maximized temporal coverage, reducing gaps that could obscure transient or intermittent phenomena. This coordination demonstrated the capacity of the global scientific community to respond to a singular interstellar event with unprecedented rigor. The intensity of monitoring also facilitated rapid hypothesis testing. As new data were collected, theoretical models were refined and recalibrated. Simulations incorporating magnetic, electromagnetic, gravitational, and quantum effects were updated daily, allowing researchers to compare predicted behaviors with live observations. The iterative process revealed subtle correlations, such as links between magnetic fluctuations and minor trajectory deviations, or between surface reflectivity patterns and spectral emissions. Each new observation added layers to the complex portrait of 3I Atlas, progressively illuminating its multifaceted interactions while maintaining the enigma of its origin and internal processes. In this phase, 3I Atlas became a nexus of global collaboration and technological innovation. The object's passage required the coordinated effort of observational infrastructure, computational power, and analytical expertise across multiple disciplines. It was no longer merely an astronomical curiosity. It had become a laboratory, a catalyst for scientific advancement, and a challenge to both methodology and theory. By observing, recording, and analyzing the object with unprecedented depth and precision, humanity was collectively probing the limits of its instruments, the scope of its theoretical frameworks, and the capacity of collaborative inquiry to confront the unknown. In this heightened observational context, every photon, every pulse of energy, and every deviation in motion became an essential piece of a vast and unfolding cosmic puzzle. The growing complexity of 3I Atlas's behavior demanded not only technical rigor, but unprecedented international collaboration. Observatories from every continent, space agencies, and research institutions coordinated their efforts in real time, creating a seamless network of observation and data sharing. Time zones and geographical distance became advantages rather than obstacles, allowing continuous monitoring that captured transient events impossible to observe from a single location. Optical telescopes in Chile and Hawaii complemented infrared sensors in orbit, while polarimetric and radar data flowed from observatories in Europe and Asia, forming a dense web of observational coverage that transcended borders. The object's passage had become a catalyst for global scientific unity. The collaborative approach extended beyond instrumentation. Data pipelines were integrated, ensuring that anomalies detected in one region could be rapidly cross-verified elsewhere. For instance, a sudden brightness spike recorded in a Japanese telescope was immediately compared with concurrent spectral data from a European facility, revealing correlations that might have gone unnoticed in isolation. This real-time synergy accelerated the pace of analysis, allowing researchers to refine models, discard implausible mechanisms, and focus on phenomena that truly challenged understanding. The workflow was unprecedented, reflecting both the urgency of capturing ephemeral events and the shared excitement of encountering a phenomenon of such rare magnitude. Scientific teams developed standardized protocols for data interpretation, with contributions arriving from multiple instruments and locations. Consistency became essential. Calibration standards ensured that measurements were comparable across wavelengths, observational techniques, and environmental conditions. Statistical models incorporated error margins from each source, creating a composite view that accounted for both precision and uncertainty. This meticulous coordination allowed researchers to identify subtle correlations among diverse datasets, linking optical fluctuations to spectral shifts or magnetic anomalies to transient accelerations, constructing a more comprehensive understanding of the object's dynamic interactions with the interstellar environment. Beyond the technical, the collaboration fostered philosophical and conceptual exchange. Workshops, virtual meetings, and rapid publications encouraged theorists, experimentalists, and computational scientists to synthesize perspectives across disciplines. Ideas flowed freely. Astrophysicists considered magnetic and gravitational models. Chemists proposed surface reactions and exotic compounds, and quantum physicists suggested subatomic interactions with the vacuum and dark matter. This intellectual convergence generated a richness of hypothesis and analysis unparalleled in the study of interstellar objects, emphasizing the multifaceted nature of the puzzle presented by 3I Atlas. The object itself acted as a unifying focus for human curiosity. The international coordination underscored the shared stakes in understanding a visitor from the stars. Its passage was a reminder of the collective endeavor of science and the universality of inquiry. In classrooms, laboratories, and online forums, the collaborative effort inspired both professional researchers and the public alike, demonstrating how the pursuit of knowledge transcends borders, politics, and disciplines. 3I Atlas, in its silent journey, had become a conduit for global connection, emphasizing that the mysteries of the cosmos are not merely individual challenges, but collective opportunities for discovery. By the conclusion of this intensive monitoring phase, the object had revealed new layers of behavior, yet remained profoundly enigmatic. The international collaboration had produced an unparalleled dataset, integrating optical, spectral, magnetic, and radar observations across time and space. Yet despite this coordinated effort, 3I continued to defy complete understanding. Its anomalous accelerations, optical oscillations, and complex interactions reminded humanity that even with global expertise and technological sophistication, the universe retains realms beyond immediate comprehension, beckoning continued observation, reflection, and wonder. As hypotheses multiplied, the scientific community found itself confronted with a remarkable divergence of theories regarding 3I Atlas. Some explanations grounded in natural processes attempted to reconcile the object's erratic acceleration, optical anomalies, and magnetic disturbances, proposing combinations of outgassing, shape irregularities, and electromagnetic interactions. Others ventured into more speculative realms, considering the possibility of artificial mechanisms or unknown natural forces beyond current understanding. Each theory was debated with careful scrutiny, evaluated against the full breadth of observational data, and modeled with computational simulations, yet none provided a fully satisfactory account of all observed phenomena. This divergence reflected both the object's complexity and the limits of human comprehension, highlighting the challenge of interpreting singular events in an incompletely understood cosmos. Among the naturalistic models, the interplay of surface composition, rotational dynamics, and magnetic interactions emerged as a leading candidate for explaining certain features. Heterogeneous surface materials, possibly including exotic ices or metallic compounds, could produce localized outgassing, generating microthrusts that accounted for some deviations in motion. Magnetic anomalies, interacting with the interstellar medium and the object's charged surface regions, could further modulate trajectory and rotation. While compelling, these models required precise conditions and could not fully reproduce the magnitude and timing of observed accelerations, leaving residual anomalies unaccounted for. The object's behavior thus retained elements of unpredictability, even under comprehensive naturalistic modeling. Speculative theories, though less conventional, remained grounded in empirical constraints. Some researchers considered the possibility of engineered structures or materials, perhaps remnants of intelligent activity, that could produce controlled motion or modulate reflective properties. While there was no direct evidence to confirm such hypotheses, the rigorously observed anomalies, transient spectral emissions, quasi-periodic optical fluctuations, and persistent deviations from predicted trajectories provided a framework within which such ideas could be scientifically explored, at least provisionally. The discourse emphasized the distinction between speculation informed by data and unsubstantiated conjecture, reinforcing the importance of maintaining scientific rigor even in the face of extraordinary phenomena. The modeling and simulation efforts supporting these divergent theories were extensive. High-fidelity computational models incorporated the object's irregular shape, mass distribution, rotational dynamics, surface composition, and environmental interactions with magnetic and interstellar fields. Each model was tested against the growing dataset, with iterative refinements attempting to match the observed accelerations, brightness variations, and spectral anomalies. The divergence of results underscored the object's complexity. Multiple mechanisms likely operated simultaneously, interacting in non-linear and sometimes counterintuitive ways. This convergence of factors rendered any single explanatory framework insufficient, demanding a more holistic approach to understanding 3I Atlas. Philosophically, the divergence of theories highlighted the profound challenge of interpreting phenomena at the edge of experience. 3I Atlas became a mirror for the limits of human knowledge, demonstrating that even with meticulous observation and sophisticated modeling, certain aspects of the cosmos remain elusive. Each theory, whether conventional or speculative, offered partial insight while reminding researchers of the vastness of unexplored possibilities. The object's enigmatic presence encouraged both humility and intellectual audacity, emphasizing that the pursuit of understanding is a dynamic interplay between observation, reasoning, and imagination. In this phase, 3I Atlas had transformed from a point of light in the night sky into a focal point for global intellectual engagement. The divergence of theories, the rigor of computational modeling, and the continuous flow of observational data created a living dialogue between humanity and the cosmos. Each explanation, Each discarded or partially validated model represented an incremental step toward comprehension, even as the full nature of the object remained veiled. The multiplicity of plausible theories emphasized a central truth. In the vast and intricate universe, mysteries do not resolve neatly, and the pursuit of understanding is as much about navigating uncertainty as it is about finding definitive answers. Supercomputers became indispensable in the effort to model 3I Atlas, translating the accumulated observational data into predictive simulations that could test the limits of known physics. Researchers constructed intricate virtual environments incorporating gravitational influences from the Sun, planets, and nearby minor bodies, magnetic and electromagnetic forces, surface composition and anisotropies, and even quantum-scale interactions and hypothetical dark matter effects. By iteratively adjusting parameters and comparing simulated outputs to real-time observations, scientists sought to identify the combination of factors that could replicate the object's observed accelerations, rotations, and optical fluctuations. Each simulation was an exercise in balancing complexity, accuracy, and computational feasibility, pushing technology to its limits. Trajectory modeling demanded particular attention. High-fidelity n-body simulations, incorporating relativistic corrections, subtle perturbations, and interstellar medium interactions, attempted to reproduce 3I Atlas's path with precision. Despite sophisticated algorithms, the results consistently revealed residual deviations, underscoring the presence of forces or processes not fully captured in the models. These deviations were not trivial. Even small mismatches in predicted versus observed positions over millions of kilometers could indicate unknown physics. Researchers treated these discrepancies not as errors, but as clues, signals pointing toward mechanisms or interactions yet to be fully understood. Optical and spectral phenomena were integrated into simulations as well. Variations in brightness were modeled as functions of rotation, shape, and heterogeneous surface reflectivity, while spectral anomalies were treated as indicators of transient or spatially localized energetic processes. By correlating these features with trajectory deviations, models explored the possibility that surface dynamics and environmental interactions could collectively produce the complex behaviors observed. The simulations revealed non-linear interactions where a minor change in one parameter, such as rotational phase or surface conductivity, could amplify or dampen other effects, producing emergent behaviors that matched the quasi-periodic and erratic patterns recorded by telescopes. These modeling efforts extended beyond reproducing observed behavior to forecasting future states. Predictive simulations suggested how the object might continue to evolve as it passed perihelion and receded from the Sun, estimating the persistence of optical and spectral anomalies and the likely magnitude of residual accelerations. By providing these forecasts, scientists could optimize observational campaigns, targeting windows of highest informational value and coordinating resources to capture fleeting phenomena. The object, once a distant point of curiosity, had become a dynamic entity whose future behavior could be partially anticipated, offering a rare opportunity to study interstellar physics in action. Beyond computational mechanics, the modeling efforts fostered philosophical reflection. 3I Atlas was not merely a test of algorithms or predictive skill. It was a lens through which humanity examined the boundaries of comprehension. The simulations, intricate and data-driven, revealed the layers of causality, interaction, and contingency that govern even small bodies in the vast interstellar environment. By engaging with these models, scientists confronted the profound complexity of the cosmos and the humility required in interpreting phenomena that operate across multiple scales and domains. Each simulation was both a tool of insight and a meditation on the intricacy of forces shaping the universe. Ultimately, the supercomputational approach underscored the object's dual role as both enigma and educator. The interplay of gravity, magnetism, rotation, surface composition, and quantum effects illuminated principles rarely observed in a single natural laboratory, while also exposing the limitations of even the most sophisticated models. 3I Atlas, through its defiance of simple explanation, became a crucible for scientific ingenuity, compelling humanity to integrate observation, theory, and speculation into a coherent, albeit provisional, understanding of interstellar dynamics. In doing so, it highlighted the extraordinary capacity of human intellect to grapple with phenomena that challenge perception, expectation, and imagination alike. Amid the technical and theoretical analyses, a broader philosophical perspective emerged. 3I Atlas offered humanity a lens to contemplate its place in the cosmos. Beyond trajectories, spectra, and magnetic fields, the object evoked profound reflection on scale, isolation, and interconnectivity. It traversed vast distances in silence, indifferent to human observation, yet its fleeting presence invited a collective awareness of the universe's immensity. The object's anomalies and erratic behaviors served as a mirror, reflecting both the fragility of understanding and the magnitude of phenomena that operate independently of conscious notice. In watching its passage, humanity glimpsed not just physical properties, but the existential resonance of being small observers in a universe governed by forces both comprehensible and inscrutable. The object's journey prompted consideration of time and impermanence. 3I Atlas had traveled for millions of years before reaching the solar system, an unbroken arc across cosmic history that predated human civilization by orders of magnitude. Observers were confronted with the ephemerality of life and knowledge relative to these timescales. Each measurement, each snapshot of brightness or spectrum, was but a brief encounter with a history that unfolded far beyond human scales. The realization evoked humility. Despite the sophistication of instrumentation and the rigor of analysis, humanity was witnessing only a fragment of a journey that extended incomprehensibly far in space and time. Simultaneously, 3I Atlas invited reflection on knowledge and uncertainty. Every anomaly, be it magnetic, optical, or dynamical, highlighted the limits of understanding. Observers recognized that mastery of the cosmos is provisional, contingent on instruments, frameworks, and interpretive models. The object's defiance of straightforward explanation encouraged epistemic humility, reinforcing the idea that science is not merely a collection of answers, but an evolving dialogue with nature. 3I Atlas, by challenging assumptions and revealing gaps in comprehension, became a teacher, demonstrating that curiosity, patience, and rigorous inquiry are as essential as data and theory. The philosophical implications extended to the notion of interconnection. Despite its isolation in the interstellar void, 3I Atlas interacted with multiple forces, simultaneously: gravity, magnetism, radiation, and perhaps even subtle cosmological influences. These interactions revealed the complex interdependence of phenomena across scales and distances. Observers were reminded that the universe is a network of relationships, where even seemingly solitary bodies participate in a vast, dynamic system. The object's behavior suggested that understanding the cosmos requires appreciation not only of individual components, but also of their interactions, couplings, and emergent properties. Finally, the object provoked contemplation of mystery and wonder. Scientific inquiry, while essential, could not resolve every question raised by 3I Atlas. Some aspects remained opaque, hinting at processes beyond current theoretical and observational capacity. Yet this opacity was not discouraging but inspiring. It reaffirmed the allure of discovery, the sense that the universe contains endless layers of complexity waiting to be understood. 3I Atlas, in its silent voyage, had become a symbol of the unknown, a reminder that exploration is both a practical endeavor and a philosophical journey, one that engages intellect, imagination, and the capacity for awe in equal measure. Through these reflections, 3I Atlas transcended the purely physical. It became a mirror for humanity's curiosity, a vessel of knowledge and uncertainty, and a prompt to consider scale, interconnection, and the profound mystery of existence. Observers recognized that the object's passage was not merely a scientific event, but a moment of collective reflection, a quiet meditation on the universe, its complexity, and humanity's enduring quest to comprehend the cosmos without ever fully mastering it. Public fascination with 3I Atlas paralleled the intensity of scientific inquiry, as images, time-lapse animations, and trajectory simulations captured global attention. Media outlets highlighted its erratic motion, pulsing brightness, and spectral anomalies, framing the object as a cosmic enigma that transcended the boundaries of science alone. The spectacle provoked a collective imagination. Social media threads, debated theories, live streams broadcast observational feeds, and educational platforms analyzed the object's behavior for students and enthusiasts alike. Humanity, collectively observing from millions of kilometers away, found in 3I Atlas both a source of wonder and a canvas for reflection on the vast, unknowable reaches of space. The narrative presented by the media emphasized drama without exaggeration, portraying the object's scientific significance while engaging the public's natural curiosity. Artists and visualizers produced renderings showing the object's elongated shape, its shimmering surface, and the subtle anomalies captured by telescopes. Animated simulations depicted its complex trajectory through the solar system, highlighting its interactions with radiation, magnetic fields, and gravitational influences. These visualizations allowed lay observers to grasp aspects of the phenomena that raw data alone could not convey, bridging the gap between specialized observation and widespread understanding. Beyond aesthetics, the public's engagement reflected a deep emotional resonance. Many individuals marveled at the cosmic journey of an object that had traversed light years before being observed, reflecting on humanity's smallness and the grandeur of the universe. Educational discussions incorporated principles of physics, astronomy, and cosmology, using 3I Atlas as a case study for teaching orbital mechanics, spectroscopy, and observational techniques. The object became a cultural touchstone, a symbol of the intersection between empirical study and human imagination, demonstrating how scientific phenomena can captivate not only minds, but hearts. Citizen science initiatives further amplified public involvement. Amateur astronomers with capable telescopes contributed observations, submitting data to centralized repositories that augmented professional datasets. These contributions, though often limited by instrument resolution, provided additional temporal coverage, especially in regions of the globe with sparse professional observatories. The collective effort emphasized the democratization of scientific observation, illustrating that curiosity and diligence could allow even non-professionals to participate meaningfully in tracking an interstellar visitor. Importantly, public engagement influenced the pace and scope of scientific communication. Researchers prepared regular updates and accessible explanations of anomalies, fostering transparency and education while preventing misinformation. By integrating public interest into scientific discourse, the object's passage became not only an observational campaign, but a societal event, highlighting the interplay between discovery, dissemination, and collective contemplation. Humanity was experiencing a rare convergence of observation and reflection, where data, visualization, and curiosity combined to produce both knowledge and wonder. In observing 3I Atlas, the public became witnesses to a narrative unfolding across millions of kilometers, guided by the meticulous work of scientists, yet filtered through imagination and interpretation. The object's journey, while fleeting, offered a profound reminder of the interconnection between discovery and cultural resonance, demonstrating that even in the depths of interstellar space, the passage of a solitary object could inspire awe, reflection, and collective engagement. 3. I-Atlas had become not merely a scientific subject, but a shared experience, uniting the world in observation, contemplation, and wonder. As observations and analyses intensified, scientists began considering potential threats posed by 3I Atlas, not in terms of direct collision, which remained exceedingly unlikely, but in terms of its capacity to challenge foundational assumptions about celestial mechanics and interstellar physics. The object's erratic trajectory, unpredictable accelerations, and anomalous magnetic and optical properties raised questions about the completeness of existing models. Could similar objects, undetected and moving through the interstellar medium, influence planetary systems or introduce previously unconsidered perturbations? The possibility, however remote, compelled careful evaluation, blending practical risk assessment with theoretical exploration. Trajectory projections were recalculated repeatedly, incorporating the cumulative effects of all observed anomalies. Scientists employed probabilistic models to estimate potential deviations, determining the likelihood of close approaches to planetary bodies, particularly Earth. These analyses consistently indicated minimal risk, with the object passing safely through the solar system. Nevertheless, the exercise underscored the importance of understanding subtle forces, as even minor miscalculations in momentum, mass distribution, or interaction with interstellar fields could produce significant changes over astronomical distances. The task reinforced both caution and respect for the inherent uncertainty present in interstellar phenomena. The assessment of potential systemic effects extended to solar system stability. Researchers considered whether similar interstellar objects, particularly those with anomalous properties, could influence orbital dynamics over long timescales. While the probabilities remained low, the calculations highlighted the interconnectedness of cosmic systems. Even small bodies, through gravitational perturbations or electromagnetic interactions, could theoretically affect minor planets or debris fields, creating cascading effects. These evaluations, though largely precautionary, enriched understanding of the solar system's resilience and the subtle forces shaping its architecture. Magnetic and optical anomalies also informed threat assessments, particularly regarding the indirect impact on observational accuracy and predictive modeling. If other interstellar objects shared 3I Atlas's properties, existing methods of trajectory estimation might be insufficient for accurate monitoring, potentially introducing observational uncertainties with practical consequences for planetary defense planning. By studying 3I Atlas in unprecedented detail, astronomers gained valuable insight into the range of behaviors possible in interstellar objects, enhancing preparedness for future encounters and refining modeling techniques to account for anomalous influences. Beyond immediate risk considerations, the perceived threat carried philosophical weight. The object's unpredictable behavior illustrated the universe's capacity to surprise and challenge even the most sophisticated predictive frameworks. It highlighted the limitations of human foresight and underscored the necessity of humility in scientific and technological planning. The evaluation of 3I Atlas's potential impact, both direct and systemic, became a microcosm for the broader challenge of navigating the unknown, an exercise in combining empirical rigor, theoretical modeling, and cautious imagination. Ultimately, the assessment revealed that 3I Atlas posed no immediate danger, yet it underscored the importance of vigilance, precision, and adaptability in interstellar observation. Its passage served as both a practical exercise in risk management and a symbolic reminder of the unpredictable forces operating across space. By quantifying possibilities, modeling outcomes, and integrating diverse observational data, scientists demonstrated humanity's capacity to anticipate and understand, even in the presence of phenomena that initially appear chaotic, unknowable, or threatening. In this way, the object's enigmatic behavior contributed not only to scientific knowledge, but to a broader understanding of preparedness and resilience in the face of cosmic complexity. Historical context provided essential perspective on 3I Atlas, situating its enigmatic passage within the broader tapestry of astronomical discovery. Humanity has long encountered interstellar or anomalous objects, from early observations of comets with unpredictable orbits to the rare interstellar interlopers documented in the modern era. Each encounter offered both scientific insight and philosophical reflection, shaping the frameworks through which the cosmos was understood. By examining prior events, such as Oumuamua and other minor interstellar detections, researchers could trace the evolution of observational techniques, theoretical models, and interpretive strategies that informed the current understanding of 3I Atlas. The first notable interstellar visitors, though sparsely observed, set precedents in both caution and curiosity. Astronomers had learned to approach unusual trajectories with careful measurement, modeling, and verification, recognizing the tendency for anomalies to provoke premature or unsupported conclusions. These lessons shaped protocols for tracking 3I Atlas, emphasizing multi-instrument observation, global coordination, and iterative modeling. By situating the object within this historical lineage, researchers could leverage prior experience while acknowledging the unprecedented complexity of the current observations. Technological evolution also played a critical role in contextualizing 3I Atlas. Early surveys relied primarily on optical detection, often limited by instrument sensitivity and observational windows. Today, a network of telescopes, space-based sensors, and advanced data processing algorithms allowed real-time multi-wavelength monitoring, producing a richness of data previously unattainable. Comparing contemporary capabilities with historical limitations highlighted not only the progress in astronomical science, but also the extent to which 3I Atlas challenged even the most advanced methodologies. Its passage illuminated gaps in understanding that persisted despite decades of observational refinement. Moreover, historical context reinforced the rarity and significance of such interstellar visitors. While the Milky Way contains countless stars and planetary systems, only a fraction of objects traverse interstellar space in trajectories intersecting the solar system. Each detection represents a unique opportunity to probe distant regions, test physical laws under unusual conditions, and evaluate the behavior of matter formed in alien environments. By situating 3I Atlas within this continuum, researchers appreciated both its novelty and its broader implications for planetary science, interstellar chemistry, and astrophysics. Philosophically, historical perspective provided humility and inspiration. The chronicles of past observations remind humanity that the cosmos often defies expectation, that extraordinary phenomena may appear sporadically, and that even singular events can reshape scientific understanding. In observing 3I Atlas, scientists were not only engaging with a unique physical phenomenon, but also participating in a centuries-long tradition of inquiry, curiosity, and discovery. Its behavior resonated as part of a continuum, linking the work of early observers to contemporary science while underscoring the enduring capacity of the universe to surprise, challenge, and inspire. Through this historical lens, 3I Atlas assumed a dual identity, simultaneously an object of immediate study and a symbol of the unfolding narrative of human exploration. Its anomalies were not isolated curiosities, but nodes in a broader story of observation, interpretation, and reflection. By integrating historical context, researchers and observers alike could calibrate expectations, refine methodologies, and situate the object's enigmatic passage within a larger cosmic and intellectual framework, enhancing both the scientific and philosophical significance of its journey through the solar system. Instrumental breakthroughs became pivotal in deepening the understanding of 3I Atlas, revealing subtleties previously hidden in observational noise. Advances in detector sensitivity, spectroscopic resolution, and real-time data integration allowed astronomers to detect minute variations in brightness, spectrum, and trajectory with unprecedented clarity. Instruments capable of capturing infrared emissions at fine spatial and temporal scales provided insight into thermal anomalies, while ultraviolet and optical sensors recorded transient features that hinted at dynamic processes on the object's surface or in its immediate environment. These breakthroughs transformed 3I Atlas from a faint, mysterious point of light into a richly detailed subject for empirical analysis. One key development was the use of adaptive optics in ground-based telescopes, compensating for atmospheric distortion to resolve fine-scale surface features. By tracking subtle changes in reflected light across rotational phases, researchers inferred compositional heterogeneity and localized energetic activity. Similarly, improvements in spectrograph calibration allowed the detection of fleeting molecular signatures, revealing both expected and unexpected compounds. These high-resolution measurements provided the foundation for testing complex hypotheses about surface interactions, outgassing, and potential electromagnetic effects, enabling a more nuanced understanding of the object's physical and chemical properties. Space-based sensors contributed complementary insights. Orbiting telescopes provided uninterrupted observation across wavelengths inaccessible from Earth, detecting infrared emission patterns corresponding to localized heating and ultraviolet flares indicative of energetic interactions. These measurements, integrated with ground-based data, allowed scientists to construct temporal maps linking rotational dynamics, reflective fluctuations, and spectral changes. The convergence of instruments across platforms exemplified the synergy between technological advancement and scientific inquiry, demonstrating how innovation could illuminate phenomena previously beyond reach. Radar and magnetometer advances also proved transformative. High-precision radar provided detailed surface, roughness, and shape models, while sensitive magnetometers detected subtle field variations associated with the object's motion and orientation. Combined with optical and spectral data, these instruments allowed a multi-dimensional reconstruction of 3I Atlas, revealing complex couplings between structure, rotation, and environmental interactions. The ability to simultaneously measure and correlate these factors represented a significant leap forward in interstellar object analysis. These breakthroughs had broader implications. By detecting minute features and subtle anomalies, they not only enriched understanding of 3I Atlas, but also expanded the methodological toolkit for future interstellar encounters. Observers could refine predictive models, test speculative mechanisms, and better assess the interplay of forces acting on small bodies traversing space. Beyond the immediate scientific value, the instrumental advances underscored the role of technology as an enabler of discovery, allowing humanity to engage with the universe at a level of precision and depth previously unattainable. Through these tools, 3I Atlas emerged, not merely as a passive visitor, but as a complex system, revealing the intricacies of interstellar physics, chemistry, and dynamics with unprecedented clarity. Amid the accumulation of observational data, patterns within the apparent chaos of 3I Atlas began to crystallize, revealing underlying regularities that hinted at subtle cosmic mechanisms at work. Though its motion remained erratic and its spectral and optical signatures unpredictable, careful analysis detected recurring phenomena that suggested a hidden structure or order governing its behavior. By examining correlations across multiple wavelengths, instruments, and timeframes, astronomers identified cycles in brightness fluctuations, magnetic field perturbations, and minor accelerations, indicating that 3I Atlas was not purely random in its dynamics, but instead operating within a framework of interacting physical forces. The identification of these patterns relied on advanced statistical and computational techniques. Time series analysis highlighted quasi-periodic oscillations in optical and spectral data, suggesting rotational or surface-driven processes. Magnetic field measurements, when synchronized with these oscillations, revealed weak correlations, implying that electromagnetic interactions contributed to the emergent behavior. Even the irregular accelerations observed in trajectory modeling exhibited subtle alignments with these cycles, pointing to a complex interplay among internal dynamics, environmental factors, and perhaps unknown interstellar forces. These discoveries marked a turning point, transforming the perception of the object from chaotic anomaly to a system with discernible, if intricate, structure. Further investigation focused on the interdependence of optical and spectral phenomena. Localized brightening events often coincided with transient emission lines, hinting at energetic surface processes such as localized heating, chemical reactions, or particle interaction. By modeling these features in conjunction with rotational dynamics and shape estimates from radar observations, scientists developed a multi-dimensional understanding of 3I Atlas's behavior. The patterns suggested feedback loops in which motion influenced energy release, which in turn affected surface reflectivity and trajectory in subtle ways, producing emergent behaviors observable across millions of kilometers. The detection of these recurring features also raised questions about the object's origin and composition. Were these patterns the product of natural evolutionary processes accumulated over millions of years in interstellar space, or did they reflect a rare configuration of materials and forces unique to 3I Atlas? The object's capacity to exhibit quasi-periodicity in multiple observable dimensions challenged conventional classifications, suggesting that interstellar objects may possess a wider diversity of structural and dynamic behaviors than previously recognized. Each detected pattern provided a clue, a piece of the puzzle pointing toward the principles governing its motion and interactions. Philosophically, the emergence of patterns within chaos underscored the universe's capacity for complexity and subtlety. Even amid apparent randomness, regularities can emerge, revealing underlying mechanisms and interconnections that are not immediately apparent. 3I Atlas exemplified this principle, demonstrating that careful observation and rigorous analysis can uncover order in seemingly capricious phenomena. The object became a testament to the layered nature of cosmic reality, where surface irregularities, magnetic interactions, and energetic processes intertwine to produce behaviors both perplexing and revealing. By the conclusion of this analytical phase, 3I Atlas had revealed itself as a system governed by intricate, interacting forces, each contributing to a tapestry of emergent phenomena. The recognition of patterns offered both insight and new questions, suggesting pathways for further study while reinforcing the object's enigmatic character. In its interplay of motion, light, and energy, the object illuminated the delicate balance of forces operating in interstellar space, providing a rare and profound glimpse into mechanisms that connect the microscopic, macroscopic, and cosmological scales of the universe. As 3I Atlas approached its closest passage to the Sun, known as Perihelion, the intensity of observable phenomena reached a peak, magnifying every anomaly and offering unparalleled opportunities for study. Optical measurements captured heightened brightness fluctuations, reflecting the increased solar illumination on its heterogeneous surface. Spectral lines intensified, revealing transient emissions that suggested dynamic processes amplified by thermal and radiative effects. Magnetic disturbances, while subtle, exhibited measurable increases, hinting at interactions between the object's intrinsic properties and the solar environment. The combination of proximity, energy input, and observational accessibility transformed this phase into a critical window for comprehensive analysis. Trajectory modeling during perihelion became increasingly sophisticated, incorporating the combined influences of solar gravity, radiation pressure, relativistic corrections, and the previously observed microthrust and electromagnetic effects. As 3I Atlas accelerated along its hyperbolic path, minor deviations from predicted trajectories were magnified, allowing precise quantification of anomalous forces. These deviations, now more readily observable, offered insights into the object's interactions with its environment, revealing the relative contributions of intrinsic and extrinsic factors in shaping motion. Researchers refined models continuously, leveraging the perihelion window to test hypotheses under extreme conditions. Surface and compositional effects became particularly pronounced during this approach. Thermal gradients induced by intense solar radiation likely caused localized heating, possibly generating transient outgassing or other energy release mechanisms. The optical and spectral anomalies observed earlier were amplified, providing clearer signals for analysis. Scientists could now correlate surface activity with rotational dynamics and magnetic field measurements, revealing emergent patterns that were previously subtle or obscured by distance. The perihelion phase offered a rare convergence of energy, proximity, and observational capability, yielding data that would remain unmatched for this object. The heightened observational clarity also enabled cross-validation of global datasets. Simultaneous measurements from ground-based and space-based instruments allowed precise correlation of phenomena across multiple wavelengths and observational modalities. Light curves were matched with spectral emissions and magnetic signatures, revealing consistent temporal patterns that strengthened confidence in the detected relationships. These correlations offered evidence of systemic interactions within 3I Atlas, confirming that its anomalies were not isolated phenomena but interconnected aspects of a complex, evolving system. Philosophically, the perihelion phase provided a striking illustration of the interplay between proximity, energy, and perception. As the object drew closer, its dynamic processes became more observable, emphasizing the dependence of understanding on both context and measurement. The heightened activity reminded observers of the universe's responsiveness to environmental conditions and the manner in which energy inputs can reveal otherwise hidden behaviors. In this fleeting window, humanity could witness, with remarkable clarity, the intricate interplay of forces acting on an interstellar visitor, gaining insights into both the object itself and the subtle mechanics governing its journey. By the end of this critical observational period, 3I Atlas had demonstrated its full complexity. Trajectory deviations, optical oscillations, spectral fluctuations, and magnetic interactions all converged, creating a dense and interconnected dataset that illuminated previously hidden behaviors. The Perihelion passage, ephemeral yet intensely revealing, underscored the value of precise timing, coordinated observation, and comprehensive modeling in interstellar studies. It was a moment in which the universe disclosed a rare depth of information, leaving observers with both answers and the enduring sense of awe that accompanies engagement with a phenomenon simultaneously tangible, enigmatic, and profoundly instructive. As 3I Atlas began its outward journey, receding from the Sun and the inner solar system, the accumulated data prompted profound reflection among the scientific community. Each measurement, each anomaly recorded over months of observation, contributed to a holistic understanding of the object, while simultaneously emphasizing the limits of current knowledge. Researchers were confronted with the duality of insight and uncertainty. The object had revealed intricate dynamics, surface heterogeneity, magnetic interactions, and spectral phenomena, yet no single model could fully account for all observed behavior. In grappling with this tension, scientists confronted both the complexity of 3I Atlas and the broader challenge of interpreting rare, transient interstellar events. Trajectory data suggested that 3 Atlas would exit the solar system with hyperbolic speed, continuing on a path that would carry it back into interstellar space. While gravitational interactions with planets and the Sun influenced minor deviations, the underlying anomalies, acceleration bursts, rotational fluctuations, and subtle trajectory shifts persisted, reinforcing the notion that intrinsic properties and subtle environmental interactions dominated its motion. The receding distance provided a moment of synthesis, allowing researchers to integrate months of observational data into comprehensive models, evaluating correlations between optical, spectral, magnetic, and dynamical phenomena over the entirety of its solar passage. The outward journey also offered a temporal lens on emergent patterns. Anomalies that had appeared sporadic during approach could now be contextualized within longer cycles, revealing quasi-periodic behaviors and interdependencies. Rotational modulation correlated with surface reflectivity, while spectral fluctuations aligned with minor accelerations and magnetic perturbations, suggesting systemic feedback mechanisms operating over multiple timescales. By examining the full arc of the object's passage, scientists gained a richer understanding of the interplay between intrinsic dynamics and environmental influence, highlighting the sophistication of interstellar objects and the subtleties inherent in their observation. Philosophically, the receding object prompted contemplation of limits, perspective, and permanence. Humanity had observed a visitor that had traveled millions of years to pass through the solar system for mere months. Yet, in that fleeting interval, it had imparted insight into interstellar physics, surface chemistry, and complex dynamical behavior. Observers were reminded of the vast scales of time and space that govern cosmic phenomena and the transience of human perception within those scales. Each discovery was simultaneously illuminating and humbling, underscoring the vastness of what remains unknown. The outward journey also emphasized continuity and connectivity. Data collected during approach and perihelion could now be analyzed in aggregate, providing a coherent narrative of 3I Atlas's behavior. Interconnections among observed phenomena became clearer, revealing systemic properties that transcended isolated anomalies. The object's passage exemplified the unity of observational science, where disparate measurements optical, spectral, magnetic, dynamical converge to create a coherent, though still incomplete, understanding of a complex interstellar system. Through this process, 3I Atlas transitioned from a mysterious visitor to a subject of enduring scientific insight, offering lessons in both physics and the philosophy of observation. Ultimately, the receding object left humanity with both knowledge and questions. Its anomalies, patterns, and behaviors highlighted the power of observation, the necessity of multidisciplinary analysis, and the persistent limits of comprehension. As 3I Atlas vanished toward the depths of interstellar space, it became a symbol of cosmic mystery, an exemplar of the subtle forces governing small bodies, and a catalyst for reflection on humanity's place in the universe. In its silent retreat, the object invited contemplation of both discovery and the unknown, leaving a lasting imprint on the collective imagination of science and society alike. As 3I Atlas finally receded beyond the immediate observational reach of Earth-based and space-based instruments, a sense of ethereal closure settled over the global scientific community. The object, having traversed the solar system with a silent, enigmatic grace, left behind a tapestry of data, trajectories mapped with exquisite precision, spectra revealing unexpected compounds and energetic interactions, magnetic anomalies that challenged conventional models, and optical behaviors that suggested both heterogeneity and dynamic responsiveness. Though much of its behavior remained unexplained, the accumulated knowledge offered an unprecedented glimpse into the complex interplay of forces acting upon an interstellar object, transforming it from a fleeting visitor into a landmark in astrophysical study. In synthesizing the months of observation, researchers reflected on the object's multifaceted nature. 3I Atlas was simultaneously a physical body with measurable mass, surface properties, and rotation, and a dynamic participant in the cosmic environment, responding to and interacting with magnetic fields, radiation, and interstellar medium in subtle ways. Its trajectory, shaped by both intrinsic and extrinsic factors, demonstrated that even small objects moving through interstellar space are subject to a delicate balance of forces, each capable of producing detectable deviations over vast distances. This realization prompted a re-evaluation of assumptions about the predictability and simplicity of interstellar object dynamics, highlighting the sophistication of phenomena previously considered marginal or negligible. The outward motion of 3I Atlas also provided a philosophical lens. Observing the object as it departed, astronomers and the public alike were reminded of the transience of human perception relative to cosmic timescales. Millions of years of interstellar travel culminated in a brief, measurable encounter, emphasizing the ephemeral nature of direct observation and the serendipity inherent in astronomical discovery. The encounter inspired both humility and awe. The universe's vastness, its capacity for unexpected phenomena, and the interplay of forces beyond immediate comprehension were laid bare in a singular, fleeting moment of cosmic intersection. Furthermore, the receding journey allowed reflection on the broader implications of the object's passage. 3I Atlas had challenged models of motion, surface composition, and interstellar interaction, revealing the limits of both observational precision and theoretical frameworks. Yet these challenges became opportunities. The anomalies, deviations, and unexplained features offered fertile ground for advancing astrophysical models, refining instrumentation, and preparing for future interstellar encounters. The object had not merely passed through space, it had catalyzed progress, inspiring innovation and collaboration across disciplines, institutions, and continents. In its silent retreat, 3i Atlas also became a metaphorical emissary. It communicated the richness of interstellar space, the subtlety of forces acting across unimaginable distances, and the persistent mysteries that define the cosmos. Its passage underscored that knowledge is iterative, provisional, and enriched through collective observation and contemplation. The lingering questions about anomalous accelerations, transient emissions, magnetic perturbations, and surface composition remain as invitations for future inquiry, ensuring that the object's influence endures far beyond its visible trajectory. As the final photons of 3i Atlas's passage faded from detection, the global community embraced a moment of quiet reflection. The object had traversed space and time, leaving an indelible impression on scientific understanding and human imagination. Its journey, simultaneously tangible and enigmatic, provided a rare convergence of empirical data and philosophical insight. Observers were left with the dual awareness of what had been learned and what remained mysterious, an enduring meditation on the beauty, complexity, and profound subtlety of the universe. In this ethereal closure, humanity glimpsed both the power of discovery and the enduring enigma of the cosmos, carried silently forward by the interstellar traveler as it vanished into the depths of space. The journey of 3i Atlas had drawn to a close, yet the echoes of its passage lingered in the minds of those who had observed it. Slowly, the tumult of data, the flurry of optical pulses, spectral anomalies, and magnetic perturbations softened in intensity, allowing a gentle reflection on the magnitude of what had been witnessed. Humanity had glimpsed a traveler from the depths of interstellar space, a solitary messenger crossing light years with a story encoded in motion, light, and energy. Though its mysteries remained partially unresolved, the collective endeavor to understand it had illuminated not only the object itself, but also the subtle forces that permeate the cosmos, from magnetic fields and quantum fluctuations to relativistic distortions and the faint whisper of dark energy. In this moment, the universe seemed both immense and intimate. Observers could appreciate the vastness of time and distance that had delivered 3i Atlas to the solar system, while simultaneously feeling the closeness brought by careful measurement, meticulous analysis, and shared human attention. The object's transient brightness, its erratic yet patterned accelerations, and the intricate interplay of its properties invited contemplation of forces both known and unknown, reminding humanity of the richness and unpredictability of existence beyond Earth. There was a quiet joy in having witnessed the encounter, tempered by humility in the face of the unanswered questions it left behind. As 3i Atlas receded, fading gradually into the interstellar void, the observer could imagine the object continuing its silent voyage, carrying with it the signatures of interaction, energy, and structure that might one day inspire future discovery. In the fading light, there was comfort and wonder. The universe, immense and unknowable, continued to reveal glimpses of its complexity, leaving those who had watched with a lasting sense of awe, curiosity, and the serene knowledge that the journey of understanding is never truly complete. Sweet dreams.